Okay, I feel like this is kind of our last lesson in a way. It's not, we'll do all the centripetal stuff, but usually friction you covered in grade 11 as well. So hopefully this is kind of a review. So friction is a force between two surfaces that prevents the surfaces from moving past each other. Um, Friction always acts opposite to the direction of motion. So that's a really key thing right there, that it's always opposite. So you can't really set it in any one particular direction with any coordinate system. You always just have to look at what the direction of motion is, or figure out what that is first. And just as a note, sometimes friction is good or desirable, right? For example, when you push your shoes against the floor to step forward, you want friction, whereas other times it's undesirable. So if you look at something like a piston inside an engine or something like that, you don't want friction. Um, and we'll get to the two parts, but I kind of want to look just a little bit at like what this actually is. I thought this was a reasonably good picture that sort of shows you where does this come from. It is somewhat from the roughness of the surface, or the two surfaces. That's part of it. And this is a sim from FET, or University of Colorado. I linked it on our course plan. But this kind of shows you also a little bit of what friction is. We've got two textbooks here, and you can't see it very well, but if I put my finger on this and move it, can you see how if you look down at the bottom, you can see the chemistry textbook. I'm actually picking it up. And it's what the big thing you're seeing, right? It's zooming in. It's trying to show you the two surfaces, like really zoomed in. So you're almost looking at the molecules that make up the two surfaces of these textbooks. And I can move it like side to side. You can see on the bottom, the book is moving a little. On the top, right, which is zoomed in, it looks like a lot. So if I set it back down and I then move one surface against the other, you can see, okay, they're sliding against each other. But what is happening to the molecules as I move it? Here, I'll move it some more. What's happening? Yeah, they're moving faster, right? That's friction, that's energy, and that comes from what we just saw. In part, that comes from the roughness of the surface, but also even just the molecules themselves and some of the attractive forces, or repulsive, right? If you look on that molecular level, there could also be some attraction or repulsion forces there that adds to them. But it really is just energy, right? It's got to go somewhere, and so often that goes into heating, and but it gives you that friction or whatever. So the two types: kinetic friction, the force of friction between two surfaces that are moving. So if you have one object moving over top of another, you're dealing with kinetic friction. Static friction, on the other hand, is the force between two surfaces that are not moving, right? So if you just push against a box like this up here a little bit, but not enough to make it move, that's static friction. In both cases, they have, you can see here this mu, the Greek letter mu here. So if you're looking at kinetic friction, you can see that letter here, mu. And so that's a coefficient. So the way you figure out the amount of friction, the actual force of friction, is you have to figure out what is the normal force. So it's always whatever the force is perpendicular to the surface. That is the force the surface is um, administering to the object, whatever you want to say. And then you multiply that by some coefficient. Right? And for static friction, it's identical, right? Whatever the force is depends entirely on, well, not entirely, I guess, depends on the normal force, but now you've got a different coefficient. And that has to do with the fact that often you have to apply a more force to get something to start moving than you do to keep it moving. So this, I thought this was a pretty good graph. It's a little bit of a simplification, but I hope it kind of makes the point. So if you have an object that's not moving, so just think about something like this box here, right? and you can see there's some applied force. So that may be from, maybe I go to the back here and I'm actually pushing it in that direction. So what happens if I just set my hands there? I don't apply any force, right? That would be like this point right here. I apply zero force, friction applies zero force, right? There's nothing for it to oppose. I apply a force of 1 Newton, right? Friction applies a force of 1 Newton, right? It opposes that force with 1 Newton. I increase my force to 2 Newtons, right? Friction responds with a force of 2 Newtons, right? It still does not allow the thing to move. Finally, I apply a force of 3 Newtons, and friction applies a force of 3 Newtons. But now friction has maxed out its ability to apply a force, right? It can't apply any more force than that. If I apply 3.01 Newtons, all of a sudden this thing starts moving, right? Friction's done all it can, or static friction has done all it can. And now we go down to kinetic friction. Now this thing is moving, and interestingly, the force of friction now is a constant, right? It's not going to be in response to whatever I'm pushing. No matter how hard I push, the force of kinetic friction will remain constant, and it will actually decrease from what the maximum force it could apply before it moved was, right? And that's just because, as I said, you usually have to apply more force. I almost think of it like those molecular forces and all that, right? It's somewhat sticking. I've sort of got a little bit of an equilibrium, but once you get it in motion, then you don't have to apply as much force to keep it moving. And so that's what we're dealing with there. One note that I thought was important about these coefficients, so whether it's mu k for kinetic or mu s for static friction, that they are determined experimentally. These aren't derived from first principles or anything like that. What you do is, if you want to know about the coefficient of kinetic friction between two surfaces, such as, wood and steel or something like that, you have to actually get those objects, get a wooden floor, get a steel box, and push it across the floor and figure this out. Right? So they come from experiment. And so that's why you usually just have to look up these numbers. Right? And here's a table just taken right out of the textbook that gives you some of these. Others you could look up. Usually on questions, though, you'll be referred to a specific table or just given the numbers because they can vary from source to source. Okay, so here we go. We got an example. We got an 80 kilogram box is tied to a 35 kilogram box with a horizontal rope. The coefficient of kinetic friction between the boxes and the floor is 0.3. So as I said, you're just given it. You pull the larger box forward with a force of 450 newtons at an angle of 35 degrees above the horizontal. Calculate the acceleration of the boxes and the tension in the ropes. So I feel like a little bit of a diagram is helpful for something like this. Here, I'll just say this is the floor. So I've got box A. And this will be the 80 kilogram box. I'll just say this is box A. And behind it is box B, which is 35 kilograms. And these two are tied by a rope. They are tied together. And box A is being pulled with a force of 450 newtons. Oh, I suppose if I was drawing it, I could draw it from the center, but I'll just leave it here. This is my applied force. my angle is. All right, that's mostly it. I suppose since these are kind of drawn like free body diagrams, I could add in some of the goodies here. I could say, well, this box, it's on a flat surface, so I'm going to have the force of gravity down on this, um, which is just going to be mg. And I'm going to have a normal force up. And I'll have the same thing on box B. I'll have mg down. And I'll have the normal force on it, pushing it down. And it's also worth noting mu k is 0.3. And so it's important here. That means I'm given mu k, so this thing is, I've got motion. It's moving. So if I want to figure out the acceleration of the boxes, can I look at this as one system? Yeah, absolutely, right? I can look at this. So as far as like part A is concerned, I can just look at this like it's one system that's moving. So I've just got a combined mass here, right? I can sort of look at this. Oh, let me change that. So for part A, for all intents and purposes, this is like, right, there's box B, there's box A, and I can just sort of look at this like it's one, just sort of one object that has a mass, if you will. I've got FG, got a normal force here. I've got an applied force. And this is my 35 degrees. And I've got the force of kinetic friction if I want to be particular here. Not that the K part matters. So I guess the first thing I would do then is look at this in the Y direction. So if I sum the forces, let me move this down. I feel like that's a bit cluttered. So looking at this system and summing all the forces in the Y direction. And in this case, they equal 0 because I've got no acceleration up or down. I've got the normal force up minus the force of gravity on the whole thing. So and so that means Fn. And I'll just, since the m total g is negative, I can move that to the other side. It becomes positive, equals the total mass, which is 35 and 80. I missed something. Just as I was looking at this, I saw that. I think that's gonna mess us up. I think I definitely skipped part of this, and I would, you can always go back at any point when you're solving and do something, right? But um, because this force here is applied only to box A, that's not going to, it's going to affect the normal force on box A, right? Because you're partially pulling it up, so that means the surface doesn't have to respond with as much, equal and opposite force. Whereas block B is completely stationary. So I would actually, we know mu, right, is the same for both. We're assuming this thing is moving, or we're told. So I would actually go all the way and just calculate the force of friction on each box, right? Then when we look at the system in total, we can just kind of add those together. So if I look at just block B and we sum the forces in the y direction, which equals 0, then for block B, I've only got mg, well, I'll say up is positive, so I've got Fn minus mg, which equals 0. So for this particular box, the normal force is just equal to 35 times 9.8, which equals 343. Then I can actually calculate the force of friction on block B, which is going to be the normal force. I don't know why I just did a big N. The normal force on block B times by the force of kinetic friction. So that's just going to be 343 times by 0.3. And I get 102.9. All right. And then I can do basically the same thing for block A. I can look at this. I'm told the applied force, though, is 450 newtons. And that I could probably resolve. And I could say, well, this component here is, because it's the opposite side, it's going to be 450 sine 35 degrees. And this part here will be 450 cos 45 degrees. Sorry. Well, my brain just decided to change that to a 4 instead of a 3. So anyway, yeah, we can sum the forces in the y direction for this box, which also equals 0. And for this, we can say the normal force is up, plus we've got the 450 sine 35 degrees minus mg equals 0. Which means the normal force is going to equal mg, which will be 80 times 9.8. So if you take that to the other side, it becomes positive. And we take this term to the other side, it becomes negative. So that's going to be minus 450 sine 35 degrees. And that gives me 525.9. Then I can do the same thing I did on the other side. I can say that means the force of friction on box A, and it is kinetic friction, but is going to be the normal force, which I just found, on A, if you prefer, times by mu K, which is 525.9 times 0.3, which is 157.77. And that will give me numbers I can actually look at here. Right? So now I can do this analysis the way that I looked at this, but when I'm looking at this friction here, right, I can say this is actually going to be the force of friction total, let's say, is going to equal the force of friction from A plus the force of friction from block B, which we just figured out, which is 102.9 plus 157.77, which equals 260.67 newtons. Okay, so now I've got a force of friction. Now I can look at this as sort of one system, if you will. And more importantly, I can look in the in the X direction, because this is the only thing I really need, which I didn't even write in here, but on the bottom, this is going to be the applied force was 450, right? That's what I actually need here. So I don't need this anymore. Now, if I just look in the X direction for this, now I can look at this as sort of a total mass or whatever. So I've got this part of the applied force pulling it forward. So and then I've got friction pulling against me, minus 260.67, and that has to equal the total mass, which is the 80 plus 35 times by the acceleration. Right. Now I just need to put in all the numbers here, cosine of 35 into a calculator times by 450 minus 260.67, and then divide all that by 115, and that will give me A equals 0.94. And that was the piece that I actually wanted for this. For part B, I'll be running out a little bit out of space here. For part B, I need to know the tension on the cable. So I definitely can't do what I did for part A. For something like this, though, I would look at, remember, for like a system, we were looking mainly at equilibrium, but for any system like this, I can always just cut it anywhere, and it has to work. So in this case, if I just look at block B, right, what is pulling block B? Then I can sort of separate this system out and just look at block B and say, block B, which is 35. Well, I've got, on this particular block, I've got a force pulling it forward. That's the tension in the rope. And I've got a force pulling it back. That's the force of tension or friction on block B, right? Only the friction on block B. And then I can just do the same analysis like I did before. I can say the sum of all the forces in the X direction for block B is equal to MA. And so that means the force of tension minus the force of friction on this block must equal the mass of this block, which is 35, times the acceleration of this block. Now, the acceleration of this block is the same as the entire system, so that's 0.94. And the tension on this block, I think I already figured out. That was the 102.9. That was the one from this one. So that means Ft minus 102.9 equals 32.9. So all I do is I cross that out and I add 102.9 to both sides of my equation, and that tells me the force of tension is equal to 135.8 newtons.